Okay, fantastic. Thank you very much. Okay, so I'm going to start. Yeah, it is with absolute pleasure that I would like to introduce today's speaker, Diego Aristizabal, to you. Diego did his PhD in Valencia, did a postdoc in Frascati, and one in Belgium, in Liège University, which is where I had the pleasure of meeting him. He was actually one of the juries on my PhD defense. And he's been in Santa Maria in Chile. That's where he has his permanent position for several years now. And today he's going to talk about neutrino physics. Yeah. Please, Diego.
Yeah, thank you very much, Venus, for the invitation. Yeah, so thank you very much as well for attending. So I was told that most of the audience here are working in theoretical aspects of different branches of physics. So that's why I kind of prepare a short introduction on the subject. Okay, so I'm going to share my screen. And okay, and so this is what I'm gonna tell you today. So physics opportunities of CEvNS experiments, and I will tell you what do I mean by CEvNS in a few minutes. But before doing that, I want to mention that most of the results that I'm gonna show today, well, not most, but this part of them are based on work I have done within the context of this new BDX drift collaboration, which is a collaboration of a kind of small collaboration of phenomenologists like myself and experimentalists, which are aiming to use directional detectors for neutrino physics. So these detectors historically have been used for dark matter detection, but now there's this idea that they can be used as well for neutrino detection, and there's this idea as well that they in principle can be used for detecting dark matter, but dark matter produced in beam dump experiments. Okay, so today I'm going to focus my talk on neutrino physics, but I will at the end will mention a few things about the possibility of producing dark matter in the laboratory and using these technologies so to detect the byproducts of that interaction. Okay, so what do I mean by CEvNS? So first of all, CEvNS stands for coherent elastic neutrino nucleus scattering. Okay, CEvNS. Okay, so this process was predicted and the cross-section was calculated long ago, about 40 years ago, probably a bit more, but it was detected only 5 years ago, back in 2017. Along with that detection, one can think about other neutrino processes and other cross-sections that have been pretty well measured in the last 20 years or so. Fermilab has a full program and has detectors which were designed to precisely measure some of neutrino cross-sections. So given that there's all this information on different cross-sections beyond the cross-section for this process, a good question to ask is, why are we interested in CEvNS? Okay, and to address that question, one has to think on the different neutrino processes that take place in different energy windows. So at the laboratory level, one can think on two energy domains, two energy regimes. There's this low energy regime where you have quite a few number of processes, of which those that matter the most are inverse beta decay, elastic neutrino electron scattering, and CEvNS itself. So this energy window goes from 10 to the minus 3 GeV up to 10 to the minus 1 GeV or so. So basically from 1 MeV up to 100 MeV. And then if you have a neutrino probe, if you have a neutrino beam whose energy goes beyond 0.1 GeV, then you have access. Basically, these processes here, they fade away, and you have access to other processes, which are the processes that I was mentioning that have been precisely measured at Fermilab and also at J-Park in Japan. So I'm speaking about quasi-elastic scattering, and resonance single pion production. So in this window, there are more processes beyond those that I'm showing here, but those that dominate this intermediate energy window are certainly these three. Okay, so what do I mean by quasi-elastic scattering, elastic scattering, and resonance single pion production? So these are the processes I'm speaking about. Quasi-elastic scattering is a charged current process induced by muon and anti-muon neutrinos. The neutrino beam in this case is such that rather than scattering off a nucleus, the neutrino is capable of scattering off the nucleons. So those nucleons are within the nuclear environment. The final state comes along a muon in the case of neutrinos and an anti-muon in the case of anti-neutrinos. And the final state involves protons, and when the neutrino beam involves neutrinos, and neutrons when the neutrino beam involves muon antineutrinos. So it is clear when you look to this process that because of kinematic constraints, a neutrino beam whose energy is below 100 MeV cannot trigger this kind of processes. So the muon mass is 105 MeV. You need a neutrino beam whose energy is above at least the muon mass. Then you have elastic scattering, which is the neutral current counterpart of quasi-elastic scattering. Processes in this case as well involve neutrinos and antineutrinos, and this is how they look like. So a neutrino hits a proton and produces a final states that involve the same neutrino and the proton, or it can hit as well a neutron, producing the same final state. That's why we refer to this process as elastic scattering. And of course, you have the antineutrino counterparts.
Sorry, Diego.
Yeah.
It's a question. So,
yeah, sure.
Why do these elastic scattering processes happen in the kind of intermediate energy region?
Because of the energy of the neutrino. So if the neutrino energy is not sufficiently high, then the neutrino probe is not capable of looking into the nuclear structure. It will scatter off a nucleus. But if as soon as you increase the neutrino energy, you are capable of looking into the nuclear structure. That is why these processes are taking place with nucleons rather than with nuclei. Okay.
Okay. Thank you.
Okay. And then you have resonance single pion production, which is a neutral current, can be induced by neutral currents or charged current processes, also induced by muon neutrinos. Here, capital N refers to nucleons in general. And the idea is the following. So the neutrino energy is such that it's not only, the neutrino is not only capable of resolving the nucleus structure, but it can produce nucleon excitation. So it produces nucleon excitation. It produces a baryon resonance, which here I'm showing with N star. And then that baryon resonance decays, typically producing pi plus, pi minus, or pi zero, depending on the final state. Okay, so this will be the process induced by charged current, and this one over here will be the process induced by neutral current. And here in this plot, I'm showing the cross section in these units normalized to energy as a function of neutrino energy for two of these processes, for quasi-elastic over here and for resonance single pion production. So a couple of comments probably are worth at this point. So as soon as the neutrino energy is above 0.1 GeV, the process that dominates in this window is the quasi-elastic process. It peaks at about 200 or 300 MeV. This peak actually people refer to as the quasi-elastic peak. And then the process, as the neutrino energy increases, fades away. And at some point, like at about 1 GeV or so, resonant single pion production kicks in and dominates up to the point at which deep inelastic scattering starts dominating. So I'm not gonna speak in this talk about deep inelastic scattering. For that, you have to increase energies very much above 10 GeV. And I'm concerned in this talk about actually the low energy window rather than the intermediate energy window. Now, these processes and the cross sections have been measured by different collaborations, but mainly at Fermilab and at J-Park in Japan. Quasi-elastic scattering was measured by Minerva. So Minerva was a dedicated experiment, which was designed to measure precisely these cross sections. So the first measurement of this process, not the first, but one of the first measurements of this process was done back in 2013 at Fermilab. And there was a follow-up measurement a few years ago by the same collaboration, Minerva, back in 2020. Elastic scattering was measured by Minibu back in 2010, also at Fermilab. And resonant single pion production has been measured both in Japan and in the US by the K2K collaboration at J-Park in 2008, the T2K collaboration in Japan as well in J-Park in 2017, and the same year, Minerva reported measurements of the resonant single pion production cross-section. So these cross-sections have been measured with a rather fair precision. So errors are probably below 10% or so. And so given that one has this information, there's a motivation for the question I'm trying to address. Why is CEvNS that relevant, given that we have other measurements of other neutrino cross-sections?
Sorry,
yeah.
may I ask a silly question?
Yeah, please.
Why does the quasi-elastic one peak around 200, 300 MeV?
You mean why is
Why is it here?
why is reaching this peak?
Yeah.
I'm not entirely sure about the answer, Venus, but I would naively say that is very likely related with some sort of constructive interference between the different components of the scatterers, which are subject to the process. I guess that is that, but I don't have a precise answer to that question.
Thank you.
Okay. Okay. And so there's this this issue about the calculation of these cross sections. So calculating this cross section is theoretically quite challenging. And even if you manage to calculate that people, of course, have done, the uncertainties in the theoretical calculation are large. So let me tell you why the uncertainties are large. So unless the target is water or deuterium, you have to take into account nuclear environmental effects. So if what you are using as a material target is iron or carbon, then you have to take into account that the nucleons are not free in that nuclear environment. They are bound within the nuclear medium. The dominant effects that have to be taken into account are polyblocking, Fermi motion, and one has to take into account the fact that it is possible for the recoiling nucleon to reinteract with the material within the nuclear environment. And in doing so, it can trigger the production, for example, of neutral pions. Okay, polyblocking has to be taken into account because what you are scattering is fermions. So you scatter fermions, you produce final state fermions. And so you have to assure that these final state fermions have a quantum state available when the scattering takes place. So that's why you have to add Pauli block. Then you have to add as well, sorry. Then you have to add as well Fermi motion, because the nucleons within the nuclear environment are not at rest. They have Fermi momentum. So when the neutrino hits the nucleus inside have a certain kinematics that you have to take into account. And then interactions you have to take into account for the reasons I just mentioned. Okay. Okay, so here, yeah.
Sorry, could I just quickly ask, is this done at like tree level, or we take into account loop effects?
No, this is just tree level calculation. Of course, one has to as well include loop quantum effects, but these are the dominant effects that you have to include regardless of whether you are doing a tree level or a one loop calculation.
Okay, thank you.
Okay, welcome. Okay, so here in this plot, just for illustration, I calculated the total cross section for quasi-elastic scattering using iron 56 as material target. And what I did was calculating the cross section first for 3 nucleons, which will be the naive calculation. So assuming environmental nuclear effects are negligible or are not there, and adding Pauli block. When you compare these results, so this is the first effect that I have here, Pauli block. When you compare the effect of adding Pauli blocking, you see that the cross section is diminished by 10%. Okay, already 10%. If I keep adding other effects like Fermi motion and reinteractions, this cross section will be depleted at least by 30%. Okay, the point is that these environmental effects are not model dependent. They are nuclear mole dependent. And since they are nuclear mole dependent, and you have to include them because otherwise you will be overestimating the cross section, then there's an intrinsic theoretical uncertainty in the calculation. Now, people have incorporated all these effects in Monte Carlo generators, which are actually used by several collaborations. Those that I'm aware of are Gini and Rowe. So these are kind of mainstream Monte Carlo generators. And even when you compare the output of these 2 Monte Carlo generators, you realize that in some cases, differences can be of the order 10% in the different outputs, 10 or 15%. So it is true that these cross sections have been measured and are to a certain degree well measured. But the point is that the predictions, the theoretical predictions, heavily rely on nuclear physics hypotheses and therefore are tricky or are challenging to have under control. Okay, let me move on to the low energy regime. In the low energy regime, the picture is completely different. You have in there processes which are very, very clean, theoretically speaking. The first one is inverse beta decay. So inverse beta decay is a process in which an electron antineutrino hits a free proton, and in doing so produces a positron along with a neutron. This process actually was the one used by Cowan and Rain in the first ever measurement of a neutrino interaction in the poltergeist experiment. And is to this day used in reactor neutrino detection. The last measurement that I'm aware of this inverse beta decay process was done in Daya Bay back in 2015. The uncertainties on the cross-section are the order of 1% that one has to compare with the other processes I was mentioning that can range up to 15%. The uncertainty is controlled mainly by the neutron lifetime. And of course, you might wonder why. Why? Where does the neutron lifetime enters here? Well, the amplitude for this process follows from the amplitude from beta decay by crossing symmetry. So the same set of couplings that determine the neutron lifetime, the vector and the axial couplings, enter in this, actually the same combination, entering this cross-section. So the values of those couplings comes from the neutron lifetime. And there's an uncertainty of the neutron lifetime that translates into an uncertainty in the cross-section for inverse beta decay, and which amounts to 1%. So the process is rather clean, and the theoretical calculation, despite being there, is not that big as in the other cases in the intermediate energy window. And then one goes to CEvNS. Okay, in CEvNS, the neutrino energy is such that the neutrinos are capable of observing the nuclear structure. So the object with which the neutrinos are scattering off is a nucleus. Since the process is elastic, so the initial state consists of a neutrino, a nucleus whose mass number is A and atomic number is Z, and the final state matches the initial state. Okay, the first ever measurement of this process was done back in 2017. It was done in the Oak Ridge National Laboratory by the coherent collaboration at the Espallation Neutron Source. And the uncertainties are comparable, theoretical uncertainties are comparable to those in inverse beta decay. They range from 1 to 5% and are dominated mainly by the root mean square radius of the neutron distribution. So you have two distributions there. I'm going to mention that in more detail later on. So you have two distributions there. You have the proton distribution, you have the neutron distribution. The proton distribution is pretty well known. The radius, the RMS radius of the proton distribution is very well known. But for the neutron distribution, it's not the case. And that's the reason why uncertainties on this process are mainly dominated by the neutron distribution. So the two processes are very clean. So one can still ask why CEvNS and not inverse beta decay. And the answer, I believe, is provided by this plot over here. So this is a calculation actually I did yesterday when preparing the talk. You can see here the total cross-section as a function of neutrino energy for inverse beta decay in yellow, and for CEvNS using as material target cesium-133. So you can see right away that there's an answer for that question. Why inverse beta decay? Why CEvNS and not inverse beta decay? The answer has to do with the size of the cross-section. So when you look to this cross-section, in a standard, let's say in neutrino standards, this cross-section is huge. Compared with the inverse beta decay cross-section, it differs by more than 2 orders of magnitude. So if you want to do precise measurements, and in addition to that, you are aiming at looking to new physics, you want a large statistics. And a large statistics is assured provided you have a large cross-section. So CEvNS satisfies this criteria. That's the reason why this process has attracted so much attention in the last 5 or 6 years. First of all, because it has been measured, and second, because you can calculate the cross-section with very low uncertainties, and the cross-section is big. So that's the answer to the first question I was trying to address. Okay, let me move on to this to this other subject. So the cross-section itself, the environments that can trigger the process, and the measurements that have been done so far. So the cross-section. Now, the object with which the neutrinos are scattering off is a nucleus. The nucleus is, of course, not a fundamental object. It's an object that has structure is determined by nucleons. Depending on the neutrino energy, the individual amplitudes of these nucleons can add up coherently. And when they do so, they enhance the cross-section. Okay. When does that happen? For what kind of neutrino energies this condition is satisfied. And to address that, you have to compare the bulk wavelength with the nuclear radius. Okay, we are enforcing this condition, and enforcing this condition implies an upper bound on the transfer momentum of that process, which amounts to about 200 MeV per typical nuclei. Now, this upper bound translates in turn in an upper bound of the recoil energy. And that information in turn translates into an upper bound on the maximum neutrino energy with which the process can be triggered. And the number you get for typical nuclei is 200 MeV. So that's the condition that the neutrino probe should satisfy so to trigger CEvNS. Okay, the cross-section actually has a very simple form. It was calculated a long time ago by Friedman in 1974. 10 years later, the calculation was redone by these people, 1984. This is the structure of the cross-section. And among the factors that one has here, there are two that play a major role. The first one is the weak charge. The weak charge determines the strength at which the said boson couples to nuclei. But then one has to take into account that that object is not a fundamental object, and that is done through the introduction of a form factor. So in reality, the strength at which the said boson couples to nuclei is not QW, but QW times the form factor. So as you increase the energy, the weak charge that the neutrino is capable of resolving reduces, and therefore the coherence of the process is diminished. And this can be seen here in this plot. So these are two example curves for xenon and germanium for the behavior of the form factor as a function of recoil energy. What you see is that as the recoil energy increases, which means we are increasing the incoming neutrino energy, the form factor starts penalizing the weak charge. And there's a point at which you enter in a deep that has to do with destructive interference of the different nucleons within the nuclear environment. Okay. Okay, so given this information, one can wonder what kind of neutrino sources one can use so to study this process. And the answer to that question is over here. So you can use, of course, reactor neutrinos. This is a typical neutrino spectrum. So this is the spectrum in these units as a function of neutrino energy. It ranges basically from 1 MeV up to 10 MeV. And therefore, neutrinos emitted by nuclear reactors are capable of inducing CEvNS. And there's, in fact, a few experiments worldwide which are aiming at measurements of that process, among which I can mention CONUS, nucleus, and ricochet. Okay. Then you have neutrinos emitted in fixed target experiments, as those used by the coherent collaboration and distillation neutron source in the US. So this is the flux as a function of energy. And here the spectrum has different components. It has what people like to call a prompt component, which is this monochromatic line, and two continuous spectra. The prompt component comes from the decay of positively charged pions, which produce anti-muons, and then the decay of the anti-muons produce the delayed components, muon antineutrinos, continuous spectrum, and electron neutrinos as well, a continuous spectrum. Energies in this case range from, at the sizable level, range from, say, 5 MeV up to 50 MeV or so. So as well, capable of inducing coherent elastic neutrino nucleus scattering. So neutrinos produced in this kind of environments are referred to as neutrinos produced by pion decay at rest, because this is actually what the pions are doing. And then you have natural sources, which can be understood as astrophysical neutrinos. You have the solar neutrino, different solar neutrino components. You have diffuse supernova background neutrinos, and you have sub-GeV atmospheric neutrinos. So atmospheric neutrinos have energies that can stand up to 10 or more GeV. Of course, in that tail, they won't induce this process at a sizable level. But those in the low energy tail, sub-GeV atmospheric neutrinos are capable of inducing the process, thus with a rate which is very suppressed, because you can see the difference between, say, boronate neutrinos and the difference between the flux of atmospheric neutrinos. Of course, the solar neutrinos involve those neutrinos producing the PP chain, but they involve as well those neutrinos involved in the CNO cycle. So nitrogen 13, oxygen 15, and fluorine 17 are those neutrinos involved in the CNO cycle, and the others are those involved in the PP cycle. All of them satisfy the condition that I have established in the previous slide. Neutrino energy is below 200 MeV. Now, in addition, then, to these sources, you might wonder where you can get other kind of sources different from these three that I have mentioned here. And this is actually the case, and this is actually what we have been trying to leverage on in the new BDX drift collaboration. So on top of neutrinos produced by pion decay at rest, you have as well neutrinos that can be produced by pion decay in flight. So these are the neutrinos produced, for example, at Fermilab in the NUMI facility. So NUMI stands for neutrino main injector, or the future long baseline neutrino facility, which will be the facility responsible for the Dune experiment. So when you look to the spectrum of those neutrinos, you see that that spectrum extends up to energies of 10 GeV or more, okay? But that spectrum has a low energy tail. If the low energy tail has a sufficient amount of neutrinos, then the low energy tail of decay in flight neutrinos will be capable of inducing the process as well. So given that the whole picture of the CEvNS program can be basically summarized in this plot over here. So you have three different energy domains in which the process can take place. So you have a domain from a few MeV up to 10 MeV, which is dominated by reactor neutrino experiments. Then you have another domain that starts from 10 MeV and goes to energies of up to 50 MeV or so, which is the domain of the spallation neutron source of those neutrinos produced by pion decay at rest. And I didn't add that here, but there's as well this project which is called the European spallation source that will be built in Sweden. And they are aiming, among others, of course, to measure that process. So here, this will be the window, experimentally speaking, of the spallation neutron source and the European spallation source as well. And then when you go from 50 MeV to energies of up to 200 MeV or so, then you are entered the domain of neutrinos produced in pion decay in flight, which is the domain of NUMI, or the long baseline neutrino facility. Okay. What about the measurements of this process? So as I said, the process was predicted a long time ago. The calculation was done in back in the 70s, with a follow-up by Stodolsky in the 80s. So one might wonder why a process that was predicted almost 50 years ago has been measured just 5 years ago. And the reason has to do with the way in which you can access the experimental information. So you have a neutrino that hits the nuclear target recoils. That's the only observable you can rely upon, nuclear recoil. For a neutrino whose energy is below 200 MeV, you don't expect a huge recoil energy. The typical recoil energies I'm speaking about are energies of the order at most of 5 keV. So you need a very, very precise detector so to do that measurement. It was actually the use of the technology developed in dark matter direct detection that enabled the first ever measurement of CEvNS. Okay. How neutrinos are produced at the spallation neutron source is shown here. So what they do is that they hit fixed mercury target with protons, which are accelerated, I think, at 2 GeV. And doing so, of course, you produce a bunch of hadrons, but mainly you produce pi plus and pi minus, along, of course, with neutral pions, which are not interesting for neutrino production. The negatively charged pions are absorbed by nuclei, but the positively charged decay at rest and produce the fluxes I just showed. They produce anti-muons, produce mu neutrinos, and these anti-muons, they further decay in this way. So the prompt component is this one, and these are the delay components. So in this kind of experiments at the spallation neutron source, you have access not only to the recoil spectrum, but you also have a timing spectrum, because you receive the signal with a delay you receive the signal from these processes, from these neutrinos, delay compared with this one. So they have two observables. They have timing and they have recoil spectra, so to deal with. Okay. The conclusion of this analysis is written over here. They observed the CEvNS at the 6-point sigma level, and data they showed is consistent with the standard mode prediction at 1 sigma. So this is how the signal looks like. So these are the data points, and this is the standard mode calculation, which I calculated myself. So this is the contribution from the different neutrino fluxes. The one in blue is for mu neutrinos, the one in red is for the anti-mu neutrinos, and the one in green is for the electron neutrinos. So this is the signal as a function of photoelectrons, and recoil energies are related in this way. So basically, you can understand this horizontal axis as an axis of recoil energy. Now, this happened in 2017. But then there was another measurement actually during the pandemic time in liquid argon by the same collaboration by Coherent, with this detector. So they got not only a measurement in cesium iodide, which was the first measurement, but they already have a second measurement in liquid argon. And I have been told that very likely they will be releasing data this year on measurements in a germanium detector. Okay, so given this landscape, I want as well to show you the different ongoing experimental efforts worldwide, trying in most cases to get a signal. So there's this experiment called CONI down in Brazil. They are using reactor neutrinos. They are using actually a research reactor for that aim. There's this other experiment in Texas, which is people in charge are from the Texas A&M University, the minor experiment using as well a research reactor. And there's a Coherent in Tennessee. Now, the advantage of using, there's an advantage, but there's also kind of a penalty factor when you try to use a research reactor rather than a commercial reactor. In a research reactor, you in principle can better understand your backgrounds because it's a research reactor, so you have the possibility of turning on the reactor in cases in which in a commercial reactor you cannot do so. But research reactors are typically way less powerful than commercial reactors. So you pay a price in the amount of neutrinos you are getting. But there's an advantage that you can place the detector much closer to the reactor core and understand better your backgrounds. And commercial reactors, of course, you don't have that flexibility. You cannot just tell the electricity company that you want to turn off all the reactor grid and live in 2 or 3 cities without electricity for 2 days because you want to understand your backgrounds. Okay, but then you have an advantage, is that the power that you get there is much higher, and therefore the flux, the neutrino flux you get is much higher. Okay, in Europe, there are various experiments as well. Nucleus is a German experiment using reactors in France. Ricochet is a French experiment using as well reactors in France. CONUS started data taking with a reactor in Germany, but that reactor was shut down last year. So now they have moved the entire experimental setup to France as well. And then you have NuGen and Red 100 in Russia, which is using reactor neutrinos as well, but liquid xenon for the detection. And then in Taiwan, you have Texon. And there are other proposals. In Argentina, people have been speaking for a while about this detector, Violeta, which will be using reactor neutrinos. In Mexico, people have been discussing this other detector called the scintillating bubble chamber, which is using the same technology used by Coop, historically by Coop and Picasso, and now used by the PICO direct detection dark matter detector. And these other 2 experiments, this one in Belgium and this one in NEO. I'm sorry. I just want to point out that this detector in Belgium is not aiming at measurements of sevens. It's actually aiming, as far as I can tell, at measurements of possible sterile neutrino states, and it's aiming as well at clarifying an issue that has been around already for a while regarding uncertainties on reactor neutrino fluxes. The reason why I think it's worth adding this detector is because, in addition to measurements of sevens, these facilities provide experimental setups that can be used not only for neutrino physics, but also for searches related with action-like particles or dark matter produced in, for example, fixed target experiments. Okay. In addition to this, yes?
Sorry, Diego.
Yes?
So is that only the case for solid in Belgium?
Yeah, as well. So they are using a reactor facility.
Mm-hmm.
And so I did an analysis a few years ago, 2 years ago, actually 3 years ago already now, in which we were aiming at showing that using reactor neutrinos, not really reactor neutrinos, but reactor facilities, along with this kind of detectors, you can in principle search for action-like particles. So the point is the following. So in a reactor, you not only produce neutrinos, you not only produce neutrons, reactors produce a bunch of photons. Okay. Yeah. So those photons, when it's scattering off the material within the core, they can go conversions into action-like particles, for example, through Compton-like processes or through Primakov processes. Mm-hmm. Now, the idea is the following. You produce the photons. These photons a fraction of them gets converted into action-like particles. And if you have such a detector, these action-like particles, if they decay in the detector, they will produce signals as those that are produced by neutrinos.
Sure.
Okay, so in that case, actually, the signal, the seventh signal, plays the role of background for this kind of searches. So it's interesting that, you know, these facilities not only provide an environment for neutrino physics, but way beyond that can be used for, as I said, searches for action-like particles or dark matter, light dark matter. Okay.
Thank you.
Okay. Now, in addition to that, one has multi-tone dark matter detectors. Here, I don't want to enter in much details. So this is the story of dark matter direct detection using liquid xenon. It started back in 2005, which what people called at that time xenon 10. That has evolved over time to what is currently xenon NT, which is using a detector with a fiducial volume of about 5 tons, aiming at this, of course, discovering dark matter and the absence of a signal to place limits on the corresponding cross-section of disorder. Now, there was for a while the discussion of upgrading xenon NT to this detector called Darwin. But then recently, Darwin and people from xenon NT and also people from Lux Zeppelin, they decided to unite and put efforts together, and they built what is now called the XLZD Consortium, which is aiming at building a generation 3 detector that will consist of about 40 to 100 tons of liquid xenon. Certainly, this kind of detectors will be capable of observing CEvNS induced mainly by boronate neutrinos, and they will be capable of as well of observing electron recoils induced by solar neutrinos, something that has been done in the past by Borexino, and actually has been done already by xenon 1T. So this is kind of the signal you expect from electron recoils, and this is kind of the signal that you expect from CEvNS. Okay.
So this 40 to 100 ton, how close will they be able to get to the neutrino floor?
They will hit the neutrino floor entirely.
That's amazing.
Yeah, entirely up to the region where the dominant background becomes atmospheric. For atmospheric to start being a concern, you need probably a detector whose fiducial volume amounts to about 1 kiloton. And this, I'm not sure will happen ever, okay? But with 100 ton, you will hit the whole neutrino floor in the region where the main background is boron-8. That will fully hit the neutrino floor.
Okay, thank you.
Okay, welcome. Then you have a summary, you know, of the physics opportunities that you have in this kind of experiments. Of course, you have the obvious thing, which is measurements, direct measurements of CEvNS and different material targets, germanium, conus, silicon and coni, coherent in argon, CSI, as they did already, but also in sodium iodide. And then you have measurements in the new BDX drift detector, if they ever happen, and different compounds, and carbon disulfide, and tetrazurine, and also in tetraethylate. And then you'll have a liquid xenon as soon as this detector starts taking data. There's something I didn't mention here. There's another project in the US, which will be using Pion decay at rest, which is called Captain Mills, and Los Alamos National Laboratory, that will be using a detector with a fiducial volume of about 10 tons liquid argon. Okay. Then, of course, you can do standard mole measurements. So all those standard model parameters that enter the cross-section can be well measured at those energies in this kind of experiment. So you can have access to the weak mixing angle at low energies. You might say, okay, what's the point? We have measured that at the set scale. So what's the point? Well, you know that this is a quantity that has an RGE evolution. So if you have new degrees of freedom, light degrees of freedom that are sneaking at low energies, they might modify the weak mixing angle at low energies while keeping its value at the set scale. So looking to this quantity at low energies makes a lot of sense, at least from my point of view. And then these measurements, which will be taking place using what people like to call the nuclear recoil channel, will be done as well at Dune, but using the electron channel. So these measurements will be complementary to those done at Dune. And then, of course, you also have the possibility of measuring the neutron distributions of different nuclei, germanium, carbon, sulfur, fluorine, and so on and so forth. And then there's this possibility I was mentioning a few minutes ago, which is looking for BSM. What is the kind of BSM one can look at? Well, you can think that neutrinos are subject to new interactions. Those new interactions can be related with our sectors, for example, in the form of effective operators, in the form of light mediators, and so on. So if you have this new interactions, they will very likely produce distortions of the recoil spectrum. So one can look for distortions of the recoil spectrum, so to tell whether these new interactions are sneaking in at those low energies. And then, as I said, one can look directly for new degrees of freedom. One can look for action-like particles produced, for example, in reactors, or one can look for light dark matter produced, for example, in neutral pion decays. Okay. Well, how am I doing with time, Venus?
We're not limited by time, so yeah.
Okay, so I think I'll tell you a few other things then.
Sure.
Okay, so I want to tell you about things that we have been doing in the new BDX Drift collaboration recently, the last 3 to 4 years. Okay, so first of all, what is the new BDX drift detector? So this detector is a low pressure TPC. It relies on a low pressurized gas, and the reason why you require the low pressurized gas is because you want to access not only measurements of nuclear recoil energies, but you also want to access the direction of the recoiling nucleus. And for that, you need a gas at a low pressure. Okay. By default, the detector operates with carbon disulfide, but it has been proven that it can operate with other compounds, such as carbon tetrafluorine or tetraethylate.
So
Okay.
sorry, Diego.
Yeah.
So why do you need a low pressure gas? Because it might distort the direction of the incoming.
Yeah, so if you have a gas at a very high pressure, then the tracks that you get are not sufficiently well resolved, so to tell in which direction the recoil took place.
That's what I thought, yeah.
If you have low pressure, then the tracks are much better defined, and so you can tell, of course, with a certain uncertainty, the direction at which the recoil took place. So it's interesting because then you have two variables or two observables, so to say. So you have the recoil spectrum, but on top of the recoil spectrum, you also have the directional spectrum.
Yeah.
So you have a measurement of two observables compared with a measurement of a single observable in conventional detectors, which provides you just the recoil spectrum. You just have the recoil spectrum, and you're aiming at, say, constraining new physics, you'll be more constrained, you will have less power than if you have two observables. With two observables, you have more power to constrain, for example, the presence of new physics.
Yeah.
Okay.
Yeah, but it shouldn't be too low pressure so you cannot reconstruct the track, right?
Exactly, yeah. So there's a compromise as well, because the smaller the pressure, the less material target you pack.
Yeah.
And the less material target you pack, the smaller your event rate. So there's a compromise, you know, what is the pressure at which you would like to operate? So in the next slide, I will show for the detector was depending on the compound, what is the ideal pressure at which it should be operated. Okay. So this is basically the idea. So you have nuclear recoils. These nuclear recoils, which mainly happen in sulfur, because I'm thinking about carbon disulfide. So you have carbon and you have sulfur. Sulfur has a larger amount of neutrons than carbon. It's a heavier nucleus, and therefore you expect the 7s cross section to be larger for sulfur than for carbon. That's why most of the events are taking place in sulfur. Now, these nuclear recoils, they induce sulfur ionization. They end up producing negatively charged carbon disulfide ions, and this charge gets drifted toward these readout planes over here, which are multi-wire. Let me remember. These are multi-wire. I think projection chambers, multi-wire proportional chambers, which are used to read the signal, okay, in the presence of an electric field, okay. So that's basically the most simple description of how the detector works. But then it comes to the calculation.
Can I just ask a quick question?
Yeah, sure.
Why are you using carbon-based gases here and not noble gases?
Why are we using carbon and non-noble gases? Okay, I'm not entirely sure about the answer I can provide. I'm not an experimentalist actually, but my educated guess will be that the operation of this detector has been proven with different compounds. And I think that the carbon disulfide compound had been proven to be the most suitable compound among those that have been proven. Okay. Other than that, I think I cannot tell you more.
Okay, thank you.
Okay, welcome. Okay. Now it comes to the determination of the signal. Okay, so this is a calculation I did back in 2021, and with a single goal. The goal was the determination of the ideal pressure at which the detector should be operated, so to maximize the signal. So here the exercise was done using a 10 cubic meter detector and with a 70 years data taking. So these are the contributions of the carbon compound, and these are of the carbon nucleus, and this is the contribution of the sulfur nucleus. As I said, sulfur dominates. Actually, where the signal peaks is basically dominated by sulfur. The signal peaks at 400 torr. Okay, so this pressure over here can be understood as recoil energy. Of course, there is no one-to-one relation, but one can translate pressure into recoil energy threshold. Okay, and this is the number of events. So the signal peaks for carbon disulfide at 400 torr, And in there you have something like 307 events, which is a rather reasonable statistics for measurements, not only of sevens, but of other different kind of physics as the one I just mentioned. Then I did the exercise as well for carbon tetrafluoride, and this is what I found. The signal peaks at higher pressures, but if I say I'm gonna operate at 400 torr, then in this case I get something like 880 events. Okay. The reason why the signal here is larger is because here you have 4 fluorine nuclei, and that factor 4 enhances the signal compared with this one. Okay. What can be done with these measurements? So people have done these things already using the cesium iodide and the liquid argon data sets provided by the coherent collaboration. Now, the idea is the following. If you want to determine the root mean square radius of the neutron distribution, you have to focus on the weak charge for a factor, which, as I told you before, enters in the cross section. Now, this weak charge for a factor you can decompose into components. One that accounts for the, so to say, proton cloud, and the other one that accounts for the neutron cloud. The form factor for the proton cloud, accounting for the proton cloud, depends on the root mean square radius of the proton distribution, while the one accounting for the neutron cloud depends on the root mean square radius of the neutron distribution. Now, for the root mean square radius of the proton distribution, information is available, and these quantities have been measured with a lot of precision, with the precisions of the order of 0.1% level, okay, using electron nucleus scattering, so using electromagnetic probes rather than electroweak processes or hadron processes. For the root mean square radius of the neutron distribution, instead, what people have done is using hadron experiments to determine their values. Hadron experiments are by definition dirty, and therefore the uncertainties for those distributions which are known are large. Okay, so using CEvNS, one can use electroweak processes to determine very precisely some of these neutron distributions. And the idea is rather simple. So you assume that in the cross-section you know everything, but the neutron distribution root mean square radius. Okay, so in that case, the event rate depends on that quantity. So once you have information provided by the collaboration, you can compare those event rates as a function of the neutron distribution with data. So what people have done is chi-square analysis following that logic, and this is the result taken from this paper from collaborators of mine, actually, of the delta chi-square distribution as a function of the root mean square radius of the neutron distribution, and this is the conclusion. Using the cesium iodide data set, and assuming that both root mean square radii for cesium and iodide are equal, which is not a bad assumption to a certain degree. They ended up with these 90% confidence limits on our end. So that quantity should range from 3.4 up to 7.2 femtometers. This is actually the first ever measurement of the root mean square radius of the neutron distribution for these two nuclei. Okay. For liquid argon data, the statistics is not that rich as in the case of the cesium iodide data, and therefore what they ended up at the 90% confidence level was with an upper bound on this quantity, 4.33 femtometers. This exercise one can do as well with the new BDX drift collaboration detector. And we did that. In this case, one has to pay attention to a bit more attention to the possible uncertainties introduced by the way in which you parameterize your nuclear form factor. Okay. There are basically two ways of dealing with the nuclear form factor. One is using ab initio calculations, but for that you have to ask your nuclear physicist colleagues. I'm not capable of doing this kind of calculations, and no one in our collaboration is capable of doing ab initio calculations. This is kind of challenging calculations. Okay, so basically everybody in this business, what we do is that we use form factor parameterizations, and the ones that are used are the so-called Helm parameterization, the Fermi parameterization, and the Klein-Nystrand parameterization. So depending on the parameterization you use, and as you increase recoil energy, the effects of the parameterization, which is a mole dependence on the calculation, increases. So this is the event rate for these three hypotheses based on different parameterizations, and the spread amounts to about 10%, more or less 10%. Of course, this is kind of okay. What are we going to do? You might think, okay, you told us before that the uncertainties are up to 5%. Well, in this case, remember that I'm using neutrinos produced by pion decay in flight. So those neutrinos can be much more energetic. They can have energies way above 200 MeV, and despite not triggering those which are above 200 MeV, not triggering the process at a very high rate, since the neutrinos are very abundant, they can contribute. And that's why there's a kind of larger uncertainty in this case. So what matter upon this? Well, it depends on the precision, on the systematics of your experiment. If your systematics are above 10%, so who cares about 10% theoretical uncertainty? Anyway, in doing the chi-square analysis, and here we did include a 10% uncertainty on the signal because of on the signal, the prediction, because of this spread induced by the different parameterizations, and these are the results of this is the result of the chi-square analysis. Our conclusion is that if we are able to run this experiment under the conditions under which we did this exercise, using the long baseline neutrino facility, neutrino beamline, and with the specifications as I already mentioned, which are a 10 cubic meter detector and 7 years data taking, the root mean square radius of the neutron distribution for carbon and fluorine can be determined with a 3% accuracy. Information for which or information which is so far not available. Okay, one can do as well measurements of the weak mixing angle using this data. So this is an example of what I did back in 2 years ago, using a different data set, the Dresden 2 data set, which is a reactor experiment which has been located actually in Illinois, and which is using a detector. They are aiming at measurements of sevens. So they claimed back in 2 years ago that they have hints for the first ever observation of sevens using reactor neutrinos. That statement has been controversial among the community, but anyway, we did the analysis, and because of the uncertainties of the quenching factor that they reported in their paper, one can basically say that there's no such measurement. You can see, depending on the quenching factor you choose, you get this value at the 1 sigma level for the weak mixing angle at scales of 1 MeV or so, or you get this other one. And when you compare these two numbers, you say, well, this is not truly a measurement. But anyway, it's just a proof of principle that using this data, you can access information on the weak mixing angle at very low energies. Okay, and the weak mixing angle can be, following this strategy as well, can be measured in the new BDX drift detector. This is the result of our analysis, and these are the conclusions that the weak mixing angle we will be able to measure at the 8% level at the nuclear recall channel using either carbon disulfide or carbon tetrafluoride. And that has to be compared, sorry, has to be compared with what DUN can achieve. So DUN can achieve a better precision, but using instead the electron channel.
Sorry, Diego, do you
Yeah.
know what is the best measurement we have of the weak mixing angle?
Is at the Z scale is provided by LHC.
Oh, okay.
Yeah. So before it was given by Tevatron data, but currently with LHC data at the Z scale,
Yeah.
the most precise measurement is done by LHC. If you move to lower scales,
Yeah.
then you have experiments such as atomic parity. Sorry, atomic parity violating experiments, which provide information on the weak mixing angle at energies of the order of renormalization scales, actually, of the order of 1 MeV or so. Okay, and which are not competitive with those values at the Z scale provided by LEC, but are certainly competitive because these are experiments which are dedicated to that.
Yeah.
Okay, so one can of course ask how well the new BDX drift detector can, so to say, compete with measurements of the weak mixing angle provided by measurements by the coherent collaboration. And this is shown here in this plot. So this over here is the renormalization scale that can be understood as the transfer momentum. So these are the values that people have derived for using coherent liquid argon data. And these are the values that people have derived of the weak mixing angle using coherent cesium and iodide. Okay, and this is the value that we calculated in this analysis that we can achieve, of course, at a different scale, slightly different scale, because these people are using coherent, are using, as I said, pion decay address, while people in the UBDX drift collaboration, we will be in principle using neutrinos produced by pion decay flight. And then other measurements that can be there, can be done, are related with the so-called neutrino standard interactions. So this is as you see, this is a dimension 6 effective operator, which involves quarks and neutrinos. So you might wonder, okay, why you don't write the gauge invariant effective operator? Well, there are two reasons for that. One is probably a historical reason. So these kind of interactions were proposed back in the 70s by Lincoln Wolfenstein. He was aiming at using these new interactions to address what at that time was called the solar neutrino problem. If you want, the new couplings here are a measurement of the strength of the new interaction, hypothetical, of course, interaction, compared with the weak interaction. Okay, that's what the first reason. The other reason has to do with the following observation. If you start with a gauge invariant effective operator, then not only constraints from neutral current will apply, you will have also constraints from charge current. And there you will have, for example, that these processes will induce where charge lepton decays will induce, for example, mu2e gamma, or mu2 electrons. And these processes are very, very constrained. So if you start with that, you know that the signals that you end up having in this kind of experiments will be tiny. Okay, so that's the reason why people in the neutrino community use this so-called neutrino standard interactions. Now, given that the new PTX Drift collaboration will be using mu neutrinos, the only parameters that can be proven are mu-dependent effective parameters. And this is the result of our analysis for carbon disulfide. Basically, the bottom line is that after 7 years of data taking, this will be the regions that can be tested with the detector, and you have to compare this with the regions that so far using cesium iodide have been proven. Okay, so this is a kind of improvement upon what Coherent has done. Okay, you know, I have.
Sorry,
Yeah,
this
sure.
epsilon e mu, so that's charge lepton flavor violating. So the constraint that you would have from CLFE processes is not as sensitive as this experiment?
Okay, so if you start with a gauge invariant formulation of this operator, those constraints coming from charge lepton flavor violating processes will be much stringent than those that I got here. Yeah.
But
if you rather start with this operator, okay, you do have charge lepton flavor violation as well. But that charge lepton flavor violation will be induced at the one loop level, so it will be suppressed. It will be suppressed.
Thank you. Thank
you.
you.
Okay, you're welcome.
Yeah.
Okay. Look, I have this other set of slides, but I don't know. As I said, you know, I have to catch a train at 5 o'clock. So
so we have time. We're a research institute. There's no teaching. But I know you have to catch a train. So yeah.
Oh, let me go through this this slides rapidly, because I think it's nice. So it has to do with the study of neutrino electromagnetic properties and what people are currently calling third generation dark matter detectors, as the one that I mentioned. Okay, so I mentioned that there's this consortium, LXLZD, okay, which is aiming at multi-tone dark matter detector. It's not that we don't have currently taking data multi-tone dark matter detectors. LZ and Xenon NT are using already from 4 to 6 tone fiducial volume detectors, but this consortium will be is aiming at way beyond that. It's aiming at fiducial volumes which exceed that by a factor at least 10. Okay. That translates into much more statistics, okay? So, of course, their aim is not that of doing neutrino physics, strictly speaking. Their major aim is looking for dark matter signals, but they will unavoidably have a neutrino background that leads to what you, Venus mentioned, the neutrino floor, okay? So can one leverage on that background? Yeah, of course, one can think of these detectors as being of dual use. One can use them for dark matter detection, but one can use them as well for precise neutrino measurements. And this is what I want to tell you in this the final part of my talk. Okay, so neutrino electromagnetic properties is okay. So very old subject, you know, studied back in the 80s by Boris Kaiser and Nieves, and these two papers. So this is how the electromagnetic current for neutrinos looks like. Of course, this requires BSM physics. Okay. The electromagnetic current is a 3 by 3 matrix, which depends upon different form factors, 4 different form factors, that this one accounting for charge, this one accounting for anapole moments, this one accounting for neutrino magnetic moments, and this one accounting for electric dipole moments. Now, since it's a 3x3 matrix, you have to differentiate between diagonal and non-diagonal form factors. The diagonal, the off-diagonal form factors are typically referred to as transitions. And for the diagonals in the zero transfer momentum limit, you have that this form factor matches what will be the neutrino electric charge. This one matches what will be the neutrino magnetic moment, this one the anapole moment, and this one the electric dipole moment. Okay, for the diagonal electric magnetic form factors, in the Dirac case, both the electric and the anapole form factors, they vanish. This has been proven by Boris Kaiser a long time ago on a general basis. This one will vanish in the Dirac and in the Majorana case as well, provided CP is a good symmetry of whatever physics you are considering. And this one, the anapole, in the case of Majorana, will be different from zero without no further hypothesis on CP. Okay, and the off-diagonal electromagnetic form factors, they are different from zero, regardless of whether neutrinos are Dirac or Majorana on a general basis. I'm assuming, of course, that you are in that physics, new physics you are writing, you are not adding new symmetries and new stuff. It's just what you can claim from this decomposition of the electromagnetic current. Okay, there's quite a few number of constraints on these couplings, but those which are more relevant apply on the neutrino magnetic moment. So the neutrino magnetic moment is the one that one can constrain better from astrophysical arguments and from laboratory experiments. So let me tell you a couple of things about astrophysical bounds, which one has to understand with care, because these astrophysical bounds, they depend first of all on astrophysical assumptions, and they depend on astrophysical, on quite a few number of astrophysical parameters, for which some of them suffer from large uncertainties. Okay, so when looking to these bounds, one has to bear in mind that, okay, there are two constraints. One comes from supernova. The first one to point that out was Raphael back in the 90s. So the idea is that this coupling flips the neutrino chirality. So you need a right-handed state, so to build this this coupling. So you know that these guys left-handed are electroweak objects, while the right-handed are electroweak singlets. So if you have this this coupling in a supernova environment, in the supernova environment, the photon will acquire an effective mass because of the medium effects. So if you turn on this coupling, then you end up having these final states, new R, new left. The new left, they get trapped in the for a while, for about 10 seconds during the supernova core collapse explosion. The right-handed, they are not trapped by electroweak interactions. They escape right away, and so they disrupt the supernova core collapse explosion. So using observations of supernova 1987A, one can place a bound, and that bound reads like this. So it's order of 10 to the minus 12 Bohr magnetons. In the stars, the idea is kind of along the same lines. So you have an effective mass for the photon. You have this new decay channel open. So photons in the stellar medium, they have a mean free path of the order of 15 centimeters. So they are trapped within the stellar environment. But when you turn on this coupling, these photons, they can emit neutrinos. Neutrinos won't be trapped in the stellar environment and they will escape. And in doing so, they will produce stellar cooling. Okay, that stellar cooling, in particular information from globular cluster stars, can be constrained and leads to this bound of the neutrino magnetic moment. Okay, as I said, this is my personal take, is that this bounds, upper bounds coming from astrophysical arguments should be understood with care. People actually, so this is an analysis done back in 2019, but there have been other analyses. Last year, there was a beautiful analysis by people from Hawaii, and they proved that if you are capable of doing a better simulation of the stellar environment, then some of these bounds can be relaxed, sometimes by factors of 6 or 7. Okay. Well, there's as well these laboratory limits, okay, which from my point of view are way more robust than those coming from astrophysical arguments, because in there you have an initial state over which you have full control. You prepare your initial state, so you have full control. Laboratory limits are divided in 2 sets, those using solar neutrinos, so all of them rely on neutrino electron scattering, and can be divided on those that use solar neutrinos and those that use reactor neutrinos. Of those using solar neutrinos, Borexino places the best bound. These are 90% confidence limit laboratory upper bounds. So Borexino places the most stringent constraint using solar neutrinos. And using reactor neutrinos, you have Texono in Taiwan, JEMA in Russia, and Camblin in Japan. And out of these 3, JEMA places the most stringent constraint, something like 3-4 times 10 to the minus 11 in units of Bohr magnitude. Okay. Okay, how does the signal for CEvNS in this kind of experiments looks like? How does the cross sections for electron scattering and CEvNS look like when you switch on this new coupling? So this is the way in which it looks for nuclear recoils, and this is how it looks for electron recoils. In both cases, you see that the recoil energy, which it is at the end related with transfer momentum, appears in the denominator. So that means that when you go to very low transfer momentum, this cross-section will grow. It will grow and it will produce spectral distortions. Okay, this behavior of the cross-section is related with the column divergence that one knows actually from classical electromagnetism. As you move towards, towards small r, the potential increases. So this is a manifestation of that behavior. Okay. The interesting thing to note here is that you expect spectral distortions if these couplings are sizable and if you are capable of doing measurements at very low transfer momentum. Okay, if you have a detector which is capable of measuring both electron recoils and nuclear recoils, then it's even better, because you can do an interplay between information coming from the electron channel and information coming from the nuclear channel. How does that look in a one-ton detector, such as the already decommissioned xenon 1T detector? So this is the expected signal, the standard model expected signal calculated. I did this calculation. So it's a very naive calculation in which I have assumed an ideal detector whose efficiency is 100%, and I have assumed no Gaussian layering. Just, the most simple calculation one can think about. And this is how the signal looks like. Okay, assuming a threshold of 0.3 keV, and a certain background hypothesis that I will mention in the next slide. This is for the signal induced by Borneo neutrinos, and then for electron recoils, this is what you get. Okay, assuming again an 0.3 keV threshold, and in this case, when you compare the different contributions, you realize that the signal is fully dominated by PP, with a subdominant contribution by the beryllium 7 spectral line. Okay. Now, what we did in this analysis was a determination of the sensitivity that third generation dark matter detectors will have to this kind of couplings. Okay. And to do so, what we did was using or generating toy experiments. So the toy experiments are, this kind of signals, very naive signals, but the signal that is expect in the standard mode. Okay. For CEvNS, we assumed two background hypotheses, 25% and 68% of the signal rate, assuming two different thresholds. And for neutrino electron scattering, what we did was using the already background characterized by the Xenon NT people and the Darwin people. So this is information which is available, so we use that information. So this, in this case, the background is mainly, in the case of Darwin, is mainly dominated by double beta decay of Xenon 136. You can see that over here in this plot.
Sorry, Diego.
Yeah, sure.
What guides you to choose the energy for these background processes?
You mean like the thresholds, 1 kV
Yeah.
and 0.3?
Yeah.
Okay, that's a very good question, Venus. Thank you. So 1 kV we did because Xenon 1T was able to do measurements with that threshold.
Oh.
Okay. 0.3 kV we did because while with these calculations, I got in touch with someone from the Xenon NT and Darwin collaboration, Kai-Xuan Ni. And he told us that they had prototypes that showed that measurements at this threshold are in principle possible. So that's why we choose 0.3 kV. Okay. Okay, so given this this procedure, then these are the results that we got. Best sensitivities in the case of nuclear recoils are found for expected for low thresholds and low background hypothesis. We did a calculation for different fiducial volumes, 1 ton, 10, and 40 tons, representative of Xenon 1T, Xenon NT or LSET if you want, and 40 tons representative of Darwin, or if you like, of the XLZT consortium collaboration. Okay. In the case of 40 tons, you see that sensitivities of the order at the 90% confidence level will be reached values of the order of 4 times 10 to the minus 11 Born magnitudes, which is very impressive because here we are speaking about measurements in the nuclear recoil channel. And these numbers are comparable to Xenon, which is used in electron recoils, not nuclear recoils. And then, of course, if you degrade your threshold, so you go to higher threshold and you have a much worse background, your sensitivity decreases, and this is shown here. Okay, it decreases by a factor 3. Okay, then if you go to electron recoils, then the situation improves even more. Okay, improves even more basically because in that case you benefit from a higher neutrino flux. So in the case of nuclear recoils, you benefit from or you use boronate, so boronate dominates the nuclear recoil signal. But in the case of electron recoils, you benefit from the PP neutrino flux, which exceeds the boronate neutrino flux by several orders of magnitude. Okay. If you go to the 40-tone case, then you realize that the sensitivity at the 90% confidence level is already comparable to the values that in principle are not ruled out by astrophysical arguments. So you will be entering regions which are not constrained by any argument. And it's interesting because it's in those regions where several TV scale models, which aim at, dealing with sizable neutrino magnetic moments, predict signals. That means that in this kind of detectors, you will be able to test or to rule out this kind of scenarios that predict very sizable neutrino magnetic moments. Okay, so I'm done with that. So I will leave here this my conclusions. I just want to point out the last thing, which I didn't have time to discuss, and is this idea of using these facilities in the search for LiDAR matter. Okay, so it's basically you collide protons against a fixed target, you produce whatever you produce, hadrons, you produce pi plus. With that, you have a flux of neutrinos, but you also produce pi zero. In certain scenarios, the pi zero, so the pi zero decays with a dominant branching fraction to gamma gamma. But if you have a dark sector and you have a dark photon there, then you can have this process as well. And if you have this process, then you can think of the dark photon decaying to dark matter. The dark matter you produce promptly after the collision of the proton against the fixed target, because that produces the pi zero. The pi zero decays right away. The dark matter propagates and then enters the detector and can produce a sizable signal. So people have discussed this, of course, but what I'm pointing out here is that in these facilities, which were not aimed to do this kind of physics, this can be done as well. Okay. Okay. Well, thank you very much.
Thank you, Diego. That was fantastic, and thank you for I know you've missed your train now. We're staying home tonight.
I'll go later. Yeah.
Yeah. No, this was really good. Yeah. Well,
Yeah.
I've had a lot of my questions, so I open the floor to whoever asks who might have questions.
So
I-
in the
Yeah, I'm sorry.
beginning, when you were saying you are doing neutrino-led collisions, I know that if you're doing lead-led collisions, you need to take into account like finite temperature effects in your quantum flow theory. Do you need to do that when you're doing neutrinos, or is that not an issue?
That is not an issue. Can you? So you said something about thermal corrections. Sorry.
Sorry, my internet cut out there. Could you say that again?
Yeah. So you said something about thermal corrections, as far as I can tell.
Yes.
So so your question is what? Is that in the proton collision against the fixed target, thermal corrections, are we accounting for thermal corrections? Is that your question?
Yeah, it's my understanding that if you're colliding lead ions, the densities are high enough that you need to take into account thermal.
Oh, yeah. Yeah, no, we don't have to take that into account because we are not concerned about the collision itself. We are interested in the byproducts of the collision. So we are interested in the charged pions which are produced in there. So you produce pi plus and pi minus. Typically, the pi minus get absorbed by nuclei, and we leverage on the pi plus that is produced. The pi plus produced will, as I said, will decay, producing neutrinos and anti-muons that will further decay, producing more neutrinos. So the collision of the protons against the fixed target, which is, I think, something also done, for example, at ALPs, I guess, at CERN, so heavy ion collisions, basically, right? That's what we are thinking about, I guess.
Yeah.
Yes?
Yeah.
Okay. It's not a far concern. It's more the byproducts upon which we leverage. Okay. The byproducts produce what we want to observe, the neutrinos. Okay.
Okay. I guess just to make sure I understood something you're saying, you said you could measure the weak mixing angle at low energies.
Yeah.
And then you could, in theory, run that coupling up to the ZMass and see if it's in agreement with the LHC data. And if it's not, then you know that there's new low energy effects that we're not taking into account. Is that correct?
No, it's not the way. It's not the way in which I'm thinking. So you have a very good measurement at the LEC, or you can think as well, measurements done at lab or measurements done at Tevatron. As far as I can tell, the leading measurement right now of the mixing angle is provided by LEC. Okay. So if you take that value and use RGE evolution, you can determine the value at low energies. Okay, through RGE evolution, assuming the standard model. And if you measure the weak mixing angle in these facilities, and there's a mismatch, then you can start wondering whether that mismatch is because of new physics, which is not accessible for some reason at high energies, but it's showing up at low energies. So that's the logic I'm following.
Okay, great. Thank you.
Okay, welcome.
Any questions, comments?
It's a rather, it was only a rather kind of experimental oriented talk, maybe.
Oh, it was fantastic. I really enjoyed it. Yeah.
Okay, great. Yeah,
Well,
that happened to me last year, that I was giving a talk in front of a 30 crowd, and I was introduced as an experimentalist, and I was like, no, it cannot be. I have made a living out of theory for quite a while.
yeah. Yes. Well, I'm going to stop recording.